Okay, well, it's a pleasure to be here. First of all, a correction. I'm not in the committee, organizing committee. Okay, they just attached my name. Because originally we were talking with Jude about this. But so I'm going to talk on identification in simultaneous equation models. And so this is an interdisciplinary conference. I'm from the Department of Economics. And so I wanted to bring more the perspective of what the advances have been in economics and related to models and analysis of counterfactuals. And just to give you a little bit of history, I might start with some quotes from Jacob Marshak's introduction to monograph number 10 of the Coles Commission for Research in Economics. So the Coles Commission started in the 30s, and it's interesting to see how it evolves from having a motto of science is measurement to a motto 20 years after that of theory and measurement. So originally they started with, let's say, monograph number 3 relates to how to work out indices, price indices in the stock market. Monograph number 10, which is this one, sets up the foundation for the analysis of simultaneous equations. Okay, and that was, so originally the first people in the Coles Commission were statisticians. Pretty much after some years, they realized that they needed theorists. So the work of theorists with the first people developed this monograph. So, I'm quoting from Malinwood, a paper on, and when he was talking about the Coles Commission, saying that basically the main achievement of the Coles Commission was the building of simultaneous equations methodology. And it was basically on this monograph. So economists have been concerned with simultaneous equations since the beginning, since this is in the 50s, and basically what Jacob Marshak says, economists are required to predict what will happen when a structure changes, when there is new rules, new, basically different, let's say, well, I'm gonna give some examples, but so they need to analyze to see what to predict this, they will need some elements that they can estimate or infer from the current situation, and for that they need data. The models involve not just the observable variables, but also the unobservable. So also there is this, to analyze, basically to get at the underlying elements, they need to understand and estimate this simultaneous relationship among all the variables, the observable and unobservable ones. So examples in economics where we need this, where counterfactual analysis is needed are, for example, prediction of prices and quantities under new law. So there is a new law, let's say minimum wages change, then what will be the new prices and quantities in all markets? What's a new product? So if a new product appears, there is a new, say iPhone appears, what will be the demand for this product? So the first model of iPhone was kind of completely revolutionary. They needed to know what was going to be the demand for such a product. How can they predict demand when the product has never been observed in the market? So that's another example of economists' work. Also calculating economic damages for illegal actions, right? So if there are two firms and one does some illegal actions, then if we need to measure what will be what was the damage to the competitor due to the illegal actions, then we do need to calculate the new equilibrium, what would have been the equilibrium if a company would not have done these illegal actions, and then calculate the profits. Now, there is also interest in economics on trying to also using structural models in order to evaluate, for example, the well-being of economic agents. So trying to recover functions that we do not observe. So for example, we might want, if as a result of a policy, some people might be better off and some people might be worse off. So how do we know who is being hurt? Or if we know that individuals we observe what they do, but we don't know what they want. We just observe what they do. So what would they be able to do? Well, what will they do in a different situation? Okay, so since agents are heterogeneous, we cannot take the behavior of one person and think that another one is going to behave like the first one, because there is all these unobservable variables that also influence the behavior. Okay. So what I'm going to talk about is first just an introduction, then since simultaneous equations are kind of like the most complicated and the most fundamental models in economics, and basically you can claim that every model is just a special case of this, I'm going to talk on the recent developments in simultaneous equation models. Just if we have time, I'll go to simpler models just to see the contract, talk about a little bit about the estimators if we have time, and conclusion. Okay, so this is kind of all my kind of like a first class in econometrics when I teach. But anyway, so we're interested in econometrics, usually in trying to get underlying primitive functions and distributions of the economic agents. And so these are, we don't observe them, but we have economic models that can match basically those variables with some observable behavior. And we can use, basically, we use those models in order to recover these underlying primitive functions. And then to predict what will happen under a new structure, we can use these underlying functions that remain stable in order to predict what will happen under a new situation. So like, for example, demand for a new product, if we need to predict the demand for a new product, we can look at what people purchase, what is the demand for existing products that have similar characteristics, try to infer from that the preferences of individuals for those characteristics, and then use them to determine what will be the choice of the individuals when a new product appears with different characteristics, okay? With different values of the same characteristics. So this is like McFadden 1974 work. And econometrics comes into play because many of the variables are unobservable, so we do need to deal with them, and those are all the variables that can create problems. We still want to get functions or distributions, and but what we observe has all this is affected by these unobservable variables. So we have a lot of work in econometrics. Now the two main developments I'm going to talk about in terms of simultaneous equations are first work on non-parametric identification of the underlying functions, and then models with non-additive and observable random terms. So in the past, it used to be that unobservable variables were kind of treated as an afterthought in the model, so an economist would specify a model, and then just because the data is not perfect, then we would just add an unobservable variable. But when we analyze structural models, there are many variables that are important, they are relevant, they determine behavior, and they are unobservable. So rather than just basically treating them as some noise, it's important to consider them as basically important variables and try to recover as much as we can of their values, okay, or at least their effect. So just to give a motivation for these unobservable models with unobservable variables, so basically if you think about an economic model, theories would specify a model, and then we confront it with the data. Some variables are observable and some are unobservable, okay? So rather than transforming the model into what we call a separable model, where we transform the economic model into one that has functions on observable variables and some other functions that depend on observable and unobservable variables. In the non-separable approach, we just leave the model as it is. We look at the original model. We don't transform it into a separable model. The separation of transforming the model into a separable one, it just depends on the data, what's observable and what's unobservable, but takes out all the economic features of the model. So rather than doing that, we just keep the original model, but now we have many unobservable variables that enter in nonlinear weights. Okay, so, but from the other side, so on one side we have a much more complicated model to analyze. From the other side we have the economic model. The economic model tells us a lot about these variables, whether they, for example, if it's ability, where it increases productivity, increases output. Right, so rather than just forgetting about it, let's use the fact that we know what is the effect of this variable, okay? And moreover, we do want to fix, so the counterfactuals, we would like to know if a particular individual or a particular company, what is that particular individual or company is going to do, the counterfactual, the individual counterfactual, rather than looking at expectation, which is an average. We want to look at a particular individual and see what would this individual do in this other situation. So every individual is characterized by a vector of unobservable variables. So if we can fix the value, can we say something about that particular individual? For a fixed value of the unobservable variables, what can we say about the counterfactual? Okay? So these are kind of the motivations for that made people work on models, non-separable models in econometrics. So just to put it in equations, so we used to look at these models, y equals x prime beta plus zeta. Then there was work on non-parametric separable models. So think about beta now as a function. So in the first model, the effect of x on y is constant. So assuming that let's say the expectation of eta given x is 0, or constant, then the change in x will generate a change for a fixed eta, a change in x in the first model. A change in x is going to generate a change in y, which is constant for all values of x. Okay? So if y is output and x is hours of work, then just increasing the hours of work is going to generate output. The change in the output is going to be the same no matter if the person works 1 hour or 20 hours. Okay? The second model is a non-parametric, so we say, well, we are going to allow the effect of the hours of work to be different possibly different for different hours of work, and then we get this model. The non-separable model says, well, there is hours of work and productivity, both affect output. So y is output, x hours of work, epsilon productivity, and then we want to look at the interaction between these two. Okay? So if we look at the second model, okay, this. So this model, so what is this beta of x? This says, well, let's look at everybody that works 8 hours, and what's the average output, assuming that the expectation of eta given x is 0. Okay, so this says what is the average output for someone that works x hours. Okay, so we average over everyone that has x hours. The second model, the third model says, well, let's look at an individual that has this output y working 8 hours. Okay, and then so the individual has this productivity epsilon, and now if we look at another individual that works 8 hours, that individual, so let's assume that this function m is strictly increasing in productivity, epsilon is unobserved. But if we observe 2 individuals, so what this model tells us is the interaction between both, right? The hours of work and the productivity. So if we look at 2 workers, they work the same amount of hours, one has more output than the other one, then that means that the productivity of the first one is higher than that of the second one, because they have more output. Okay, so we have this function. So as you can see, this simple model where we just put them together and allowing some, basically using the model that productivity increases output for a fixed x, allows you to say a lot about epsilon, okay? So looking at two people, two workers, I can say, and the output, I can say who has more productivity and observed productivity than the other one, okay? So this is a very basic model that has been studied. Now we can consider more complicated models, simultaneous equation models. So in simultaneous equation models, we have y1 is affected by y2, and then so we're assuming that the y's and the x's are observed, the etas are unobserved, and the betas and gammas are parameters, are fixed parameters. So in the linear model, this is a standard specification of a simultaneous equation model, textbook example. Now, the non-parametric, non-separable version would be this one, okay? So if you think of y1 is the quantity demanded, y2 is price, x1 is income, and epsilon 1 is taste for the product. Okay, so this is, so we have this model. So the more we like the product, when everything is fixed, the more people are going to demand the product. And then on the second equation is the supply. So the price that producers want to ask if they have to produce y1, the quantity, given x2, which are the wages or some other input cost, and epsilon 2, which is a productivity shock, then that will be the, right? So this is the supply equation. And what we observe is the solution of these equations, which are price and quantity as functions of the x's and the epsilons, okay? So but this is the model we would like to know, and then we want to know, for example, we want to know what happens if we can identify this, or at least the derivative of M1 with respect to Y2. So if this is quantity and this is price, then that will tell you what will be the infinitesimal change in quantity demanded for a change, that's the partial derivative, so for a change in price when X1 and epsilon 1 stays fixed, okay? Okay, so that's it's possible to identify this under certain restrictions I'm going to talk about. Okay, now a simpler model, a model in between, is the triangular model, which is a recursive model, right? So for example, the textbook example is wages or lifetime income. So Y1, right, let's say wages is a function of years of education, Y2, and productivity. Okay, so wages is a function years of education and productivity. Now, as we know, these two are correlated. They are not independently distributed because an individual, when thinking, years of education is a choice, right? So every time that we have an individual making a choice, then that individual is going to consider many variables that we do not observe and the individual observes. So the individual is going to observe at the time of making the decision how many years to study of some measures of his or her ability, okay? So we don't observe them, but we know they are there. So we know, and that measure of ability is going to be a predictor of the productivity. So, so that is going to influence both Y2 and eta 1, okay? So what do we do? Well, the standard approach is to look for what we call an instrument, this X2. So that will be, for example, years of education, distance to school, something that exogenous that makes people differentiate. People with the same, let's say, an observable will choose different Y2s. So let's say that this is cost of education. So years of education is a function of cost of education and something which is unobservable, but we can think of this signal of the productivity, which could be grades. Okay, so the individual observes this. The individual observes the signal of the productivity, the cost of education, yes, and decides how many years of education to take. Okay, so that's Y2. So we can solve this system. Okay, and then once we have this system, then we can estimate this, which was the signal for this eta 2, conditional on that these two are going to be independent, and then we can estimate the first model. Okay, so this is the standard way. Now we can do the same with a non-parametric, non-separable model. Okay, so we can do this, right? So now we have this eta 2, so this can be estimated, assuming that this function is, so these are all non-parametric and known functions. The only assumptions are that they are strictly increasing in the unobservables. Okay, so this is a recursive model. We estimate this model. We can identify this model. We get eta 2. And then conditional on eta 2, these two are going to be independent. Okay, I did this. Okay, now there is a relation in linear models. Actually, you can, if you have a simultaneous equation in linear models, you can, okay, that was, sorry. Okay. Yeah, so in linear models, you can estimate a linear simultaneous equation by first transforming it into a triangular model. In non-parametric, non-separable models, you cannot do that. So every time, so once we come out of the framework where everything is linear and additive, lots of complications appear. So for example, in textbooks in econometrics, there are many methods to estimate simultaneous equation models when they are linear and additive in the unobservable random terms. All these methods are completely different when you relax the linearity. So, and in fact, if we can ask the question, well, if we have a simultaneous equation model like this, when is it observationally equivalent to a triangular model like this, okay? So there are very strong restrictions in this model under which these two are observationally equivalent. Okay, so in fact, most times you cannot do that. But of course, one possibility is to estimate the simultaneous equation model, estimate the derivative of M2 with respect to Y1, and then test whether that's 0 or no. Okay, so that's okay, so some reference, how are we? Time? Okay, so models with simultaneity have been considered there are different approaches. One approach is extending what we could do in linear models. So for example, if you have this model, y1 is a non-parametric function of y2 plus epsilon 1, there is also a non-separable version of this. So think about taking an instrument x, so that the expectation of epsilon 1 given x is 0, okay? Then we can basically write how the expectation of y1 given x, so the expectation of m1 y2 given x, which is going to become this, and the expectation of epsilon 1 given x is 0. So basically we have this, so we're interested in this function, and we have this integral equation. Now integral equations are difficult to estimate, and also like basically, this work mostly assumes that there is a unique solution to this. So basically, identification is not dealt with. So this is observed from the data, right? So this can be calculated from the distribution of y1 and x. This is the conditional density of y2 given x. That can be, again, calculated from the data. So this is observable. This is observable. So we just need to solve for this equation, okay? Now, a different approach is a transformation of variables approach, which is an approach that I have followed. And so this imposes some restrictions on the function, but at least we know that, but most of them are testable anyway. So first we do want that x, the observable variable, be independent or conditionally independent of the unobservable variables. We have some conditions on the density or the function, and an important, basically a critical, more or less assumption is invertibility, at least local invertibility, which means that if we observe a vector of y's, and we know that it's generated from a vector of epsilons, then there is a one-to-one relationship between these two. Okay, so we don't know what is the epsilons generating a y, but we know that it's unique. Okay, and that's important. It's the same as with the productivity. When y was product, x hours of work, and epsilon was productivity. So we know that we don't know what the value of productivity is for a particular individual, but we know that it's unique. Okay, so there is a one-to-one relationship between output conditional on x. For everyone that works 8 hours, people that have more output have more productivity. Okay, so that's it. Okay, and then under these assumptions, we can basically write the transformation of variables equation, which says that, so given the values, observable values for the y's, which we call the endogenous variables, and x, which we call the exogenous variables, which are the variables determined outside the system. So given values for y and x, this R tells us what would be the value of epsilon, of the unobservable variable, okay? So of course this function is unknown, but we model it this way. So this tells you what are the values of the unobservables that correspond to a particular y and x. And this is just the Jacobian determinant of that function. And this is the density of the epsilons conditional on x, and we might have some other things. This is very general. Of course, if we assume that epsilon is independent of x, this x disappears, right? And this z can be added or not. Okay, so just to give you an example, so consider a consumer that has taste epsilon 1. So a consumer has to choose, has a budget, has an income, I, okay, some amount of money, and has to choose how to divide this budget between how much to spend in food, how much to spend in services, and everything else. Okay, so Y3 is everything else, Y1 will be food, and Y2 is services. Okay, so standard microeconomic theory 101 tells you the consumer maximizes utility, this function U subject to the budget constraint. Okay, so if we solve the system, the first order conditions that Y1 and Y2 have to satisfy, so Y3 is basically determined by the budget, the conditions that Y1 and Y2 have to satisfy in order to be the optimizers of this problem as a system of simultaneous equation. Okay, so an individual is going to choose simultaneously how much to spend in food and how much to spend in services and something else, okay? So, and this is a function of food as a function of E1, the taste for, so this is the taste for food, and this is the taste for services, okay? So the functions, if we solve the equation, so an individual that has particular tastes for food and particular taste for services is going to want to spend this amount of, is going to have this food quantity, okay? If we put the demand for services, that's going to be the other equation, okay? And then so for particular values for E1 and E2, we're going to have different values of Y1 and Y2. Okay, now this is, let's look at all the individuals that demand for food Y1, fixed, okay? So let's look at everyone. Now, we have two individuals that they, basically you can observe them choosing the same amount for food, but we know that they are different, potentially different. They have different tastes, okay? So how do we compare them? So if we try to go back to their tastes, okay? So what will be the taste of these two individuals? So this tells you basically the level set of the taste, epsilon 1 and epsilon 2, that correspond to individuals that choose a fixed amount of food, Y1, okay? So this is Y1 is fixed, okay? So if we look at an individual that, so let's compare these two individuals. So this has a low taste for food and this has a high taste for food, okay? So how is it that they both purchase the same of food? Well, this individual with a high taste for food also has high taste for services, okay? So it has to compensate. So you can see the simultaneity. So one thing affects the other one, okay? Now we can do the same for services. So the blue line corresponds to the values of the taste for food and taste of services for people that spend a given fixed amount of services, okay, Y2. And now, so what we want basically is to look at, to know how these functions change, right, with taste, with prices, with income. So the method, the transformation of variables equation method, is basically saying, well, we can look at these basically derivatives, okay, by looking at the derivatives of these functions. Now what do we do? Well, let's change. So let's add 1 unit of food and 1 unit of services and do the same thing, right? So this is telling you how the epsilon, how the taste change, right? So from someone that purchased Y1, or Y1 equals C, to someone that purchased Y1 equals C plus 1, okay? So those are the other lines. Okay, and this here is telling us basically, so these are the tastes, right? So this is the change. This is the taste of people that will increase consumption of food and services, okay? Okay, so these are the vector of taste for food and taste for services of individuals that will purchase basically quantities of food between Y1 and Y1 plus some constant, and Y2 and Y2 plus some constant. Okay, so basically now we're mapping the change in consumption to a change in taste. So this is the relationship that we have, basically. So we want Y1 and Y2 are going to be functions, as you saw, of epsilon 1 of the taste for both of them. And we have this transformation of variables equation. So and now the question of identification, which means how can we recover elements of the demands or the distribution of taste from what we observe. Well, what we observe is this, the distribution of food and services purchased. And so on this side, everything is observed. Basically, here, nothing is observed, right? So the density, the distribution of epsilons is going to influence the distribution of demand and or choices, and the map between the demands and the epsilons, which are these ones, they are also going to influence this, okay? So what we observe, the distribution of choices. So on a budget set, let's say we're going to have a distribution, different people are going to choose different quantities, and that will depend on their taste. There is a distribution of this taste, which we do not know, but they generate this distribution of the budget set, okay? And then, of course, there is these utility functions, the original ones, that are going to also determine the relationship between how this taste affect the choices, okay? So we would like to get all this, and of course, we only observe this one, okay? So what do we do? Well, as you can notice, it's very highly nonlinear. So there are many strategies that have been studied to deal with these problems. We can, of course, add additional observable variables that will separate the influence of one from the other. A linear representation I'm going to talk about. We can know something about these functions. Are they unimodal? Okay, are they, separable in some variables? So we can use that. So we don't need to go out to the original approach was, let's assume everything is linear, maybe even imposing a distribution for the unobservables. So now we're trying to see how much we can go to the other way, basically, without imposing much. So we have exclusion, restrictions, independence conditions, okay? And just to give you, so think about, to give you graphically one of the solutions. So think about this function, okay? So let's say this is the demand for a product, and we would like to know, so Y1 is quantity and Y2 is price, we would like to know how the derivative of this function. So if we change the price when everything else is fixed, right, so how will the demand change, okay? What we have is, of course, we don't observe this demand. We observe the intersection of this demand with the supply equation. So let's put the supply equation that intersects at that point. Okay, so we observe Y1 and Y2, not as elements in a function, but just as the intersection of two curves. Okay, and we want the slope of this one. So what do we do? Well, the standard approach, the original approach in linear models was, let's think about an instrument, some x, wedges, that we observe, that will move the supply equation up and down. Okay, so we have all these intersection points, and if since the intersection points all fall into the demand equation, then we just use those intersection points to get at the slope. But of course, this function is nonlinear. So if we do that, we are going to get a slope that is very different from the true one, okay? So the approach is basically to transform the model to get a linear transformation, okay, of the simultaneous. So if we look at the transformation of variables equation, it's a way in which we can transform it by some taking logs and taking derivatives into a linear expression. And then, so in the linear expression, we're going to have, so now, okay, if we come back here to this function, so you can see this, we are interested in this slope, which is very characteristic only to y1, y2, okay? So we don't want to move to go to look at values that we get at intersections of demand and supply for different values of y1 and y2. So this has to be local, okay? So we just look at y1 and y2, fix that, okay? And then, so we're going to have a linear equation where the slope, so this is going to be a transformation of the conditional density of y given x, okay? And this is also another transformation, but the y's stay fixed. So we fix y, and then we move x's. And then basically the idea is we move the x's, which would be, let's say, wages of, or some other input cost, and then we try to see what is the effect of that on the distribution of y given x, okay, of the prices and quantity given x. So when we move x, this line, basically it has the slope that we want, is going to move up and down, okay? And different values of x are going to be points on these lines, okay? So the effect of moving x in this transformation is going to be moving this line in parallel, up and down. So all these lines will have the same slope, okay, which is the slope we want. And now the crosses are observations, okay? So different values of x. So we know this. So if we know the distribution, we can, these are not random. I mean, basically we know. So, I mean, if we observe the x's. So now, if we want the slope and they are all parallels, then you can see here, there are two crosses on one line. All the lines have the same slope, which is what we want. So we can use these two crosses and just, calculate the slope, right? We know that the two are in the same line. We want the slope of the line, so we can calculate, right? So we look at the values here over the values here. This is observed, the crosses are observed, and then we do this, okay? So we can calculate the slope. Okay, now if we have two instruments, one for the demand and one for the supply, we're going to have lines for the demand that move in parallel and lines for the supply that move in parallel, and we can do the same, basically. We want the slopes of both of them. We have these observations, okay? So that's basically geometrically what's going on. The example I gave you was for a model like this. So it has some additional structure, which is having these x's plus epsilons together, okay? We can add more x's, but basically. And in fact, if we have for one equation, we don't need, if we are interested in the derivative of the demand with respect to price, we don't need x1, right? Basically, we can identify. Okay, and so this is the linearization that I was talking about. So basically, so what we observe is this, the derivative. So we observe this, the density of the endogenous variables, y1 and price and quantity, conditional on x, income and wages. Okay, so this is what we observe, I mean, in the limit, right? So, so we can estimate it from the data, non-parametrically. So we observe this. We can take the derivative, take logs and take derivatives with respect to either y or x, so this is w, and then these are the GW. So basically you end up with something like this. This is just looking at the transformation of variables equation, taking logs and taking derivatives and solving. So so this is the taste for, let's say, okay, so if this is food, so this is, let's say, in the supply and demand. So this will be, R1 is the taste for the product. So how the taste of the product changes when Y1 is the quantity changes. And this is how the taste of the product changes when the price changes. Okay? So we're trying to infer these unobservable variables. Okay? And the derivative of the demand with respect to price is basically the ratio. is the ratio of these two things, R1, Y2 over R1, Y1. There is a typo, you can see. Okay, so this is R1. This should be R2, Y1, sorry. This is R2, Y1, okay. Hmm? 5 minutes, okay, good. Okay, so if we have a model like this without just, we're interested in the derivative of the demand with respect to price, then I have developed an estimator, I mean for that and for the previous one, that so we can identify this and we can estimate it. Okay, so the estimate, so basically we look at the density of price and quantity given wages, and taking logs, derivatives, and solving that system, basically we can, right, so here the GX1, GX2, GY1, GY2, they are observed. And under this particular separability, the R1Y1, R2Y1, R1Y2, and R2Y2, they are, and these, they are fixed, they are like coefficients. Okay, so basically we transform, rather than we have this nonlinear system, we transform it into one with basically a linear with constant coefficients. The coefficients are constant for a particular value of y, and the rest are basically variables, but rather than observing x, rather than putting x, we put this function, this transformation of the density. Okay, so there is one can estimate this derivative. So as you can see, the derivative depends on, let's say if this is a demand equation, this depends on the price and a particular value of epsilon 1. Okay, so we're looking at a market where people have a particular taste for the product and a given price, and we're asking, okay, so if we fix the product, if they have exactly the same taste, and we just change the price a little bit, what will be, how much more they will want to demand? Okay, so this is the counterfactual. So again, it's for a fixed value of the epsilon 1s. How do we know that? Do we know the value of epsilon 1? No, but we say, okay, so we know that for a given price, if we observe a given quantity, there is a unique value of this taste that corresponds to that quantity. Okay, so, and now we want to see what happens if leaving the taste fixed, we just change the price of only the demand. Okay, so that will be the counterfactual. Okay, so so this is more or less what I wanted to say on simultaneous equations. I just, for those of you that are not familiar with the literature on non-parametric, non-separable models, I just wanted to give you then a survey of what exists. So the first model was Y is M x epsilon, where x and epsilon are independent. So that will be so think about output is Y, x hours of work, epsilon is productivity. Second model was the one with triangularity, where we can estimate this model recursively. Okay, so first we estimate the second one, Y2 years of education as a function of cost of education and some signal of the productivity, and then we estimate the first one. Non-separable models are for simultaneous equations, they can have two instruments or one instrument, it just depends, okay? And there is lots of references, many people work on this, models with simultaneity, triangular models, and non-additive models, if you are interested. And just to give you for the basic model where x and epsilon are independent, so basically we have this, so in the simultaneous equations we need to deal with the densities, but for the other two models, the basic model with independence and the triangular model, we can deal with conditional distributions, which are much easier objects. So, so if x and epsilon are independent, then we have this relationship, right? The distribution of epsilon, right, can be written in this way. This is the distribution of y at this function m x epsilon. And if we take derivatives on both sides, so remember this distribution is known, right? So this we can estimate, okay? And these two, so we have here an equation, functional equation, where one function is known and these two are unknowns, okay? So what can we do? Well, we have two functions that are, we cannot get two functions out of one, but maybe we can ask, well, what can we get? And one of the important things is what is basically the counterfactuals. What happens if we vary x fixing epsilon, okay? So if we look at a worker that has a given productivity, fix the productivity and just make him or her work a little bit more, what will be the change in output, okay? So that we can say, without specifying anything about this distribution, basically just take derivatives on both sides with respect to y and x and solve, and this is what we get. Okay, so as you can see, the counterfactual, the effect of changing hours of work for a worker with productivity epsilon, which we do not know, but we know that corresponds to the output that we observe. So we observe a worker with output and hours of work. Then we say, okay, so if we fix the productivity and change the hours of work, by how much output will increase? So this is the infinitesimal change, and this is the finite change. So we change from 8 to 9. Okay, so again, we can solve these equations and obtain this. So we observe him or her with this output, and this will be the change. Okay, so we can talk about changes, basically counterfactual changes within this very flexible models that do not impose restrictions like linearity or other parametric structures, and they allow for individual counterfactuals. So we fix the value of an observable variables. We want to know what will happen when we change a variable. Okay. So I think I stop here. Okay.